Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video on extremes on an interval. What you'll be able to do by the end of this video is take a function like this and calculate its maximum and or minimum value on a given interval like this. So whenever we're talking maximum or minimum value of a function, we should straight away think of the first derivative. So as we've learned in previous lessons, possible local maximum or minimum occur when the first derivative is equal to 0. So if this derivative is equal to 0, I have a quadratic equal to 0. So you can use the quadratic formula or do what I'm doing here, which is factorizing. So I took out a common factor of 6, and then I just need to find two numbers that multiply to 8 and add to -6, which is of course -4 and -2. And now using the null factor law, either the first bracket is equal to 0 or the second bracket is equal to 0, which would mean x equals 2. So at x equals 2 and x equals 4, that's where possible stationary points occur. So substituting in each of these values, f of 2 gives me the value 39 and f of 4 gives me the value of 31. So we could apply the first derivative test to determine whether each of these points constitutes a maximum or a minimum, but we can probably tell that this is going to be a maximum turning point and this a minimum turning point. So you might be tempted to stop here and say, okay, the maximum value is going to be 39 and the minimum value is going to be 31. Not so. Remember, I referred to these points as local maximum or minimum, and that's the case with any function. Its stationary points are not necessarily global maximum or minimum, just local maximum or minimum. So you're probably thinking, well, what am I talking about? Well, let's just draw a really rough sketch of this graph to see what's going on. So the function's going to have this maximum turning point here at x equals 2 and a minimum at x equals 4. But what's going to happen after these? Well, as x gets larger and larger, the function is just going to get larger and larger. As x approaches infinity, the value of this function approaches infinity. So it's just going to go on and on forever up there. And before this turning point, as x approaches minus infinity, the function just gets smaller and smaller. So it would end up going all the way down to infinity like that. So this is just a rough sketch of this function. So we can see that this value here, f of 2 equals 39, it's not the maximum of the whole function. It's the maximum sort of in this neighborhood, in the neighborhood of 2. It's the largest value. So that's why I called it a local maximum. And similarly here, this isn't the minimum of the entire function. It's going to have a much lower value when x is in the negatives. But this value here of 31 is the lowest value of the function in this neighborhood. So all of this means that we can't just assume that the two stationary points, or any stationary points we calculate, are the maximum and minimum value of the whole function. So how do I check the maximum and minimum value of a function on a given interval? Well, you do what we did and calculate the stationary points, but you also need to check the end points of the interval you're given. We need to check the value at x is 1, and we need to check the value at x is 6. So we need to check these two blue points here, which are the endpoints of the interval. So all I need to do is substitute them into the original function. So if I substitute f of 1 into the original function, I get 31. If I substitute x equals 6 into the original function, turns out I get 71. So at x equals 6, there's a much, much larger value of the function than when x was equal to 2. This is only a local maximum. This is a much larger value. So we conclude that the maximum value of this function on the interval is 71 and the minimum is 31. So when you're trying to find the maximum and minimum value of a function on a given interval, you need to check both the stationary points and the end points of the interval. So now what we're going to do is rub out all of this working out and calculate when the value of this gradient will be a minimum. So to determine when the gradient of this function is at a maximum or a minimum, I'm essentially finding out the minimum and maximum value of this function on this interval. So the process is the same. I'm going to differentiate this and find its stationary points. So if I differentiate this, I call it f double dash x. That's the second derivative of my original function. It's the derivative of the first derivative. So the derivative of this, we don't do it any differently than we've been finding derivatives for the past few lessons. We get 12x minus 36. So this function is 0 when x equals 3. You just solve the equation 12x minus 36 is equal to 3. So at x equals 3, we're going to substitute that into this red function here. So if I put in f dash of 3, I get minus 6. But as I explained before, we can't just assume that this stationary point will give us the maximum or minimum value. I must also check the endpoints of the interval. So f dash of 1, substituting 1 into this function here, substituting in the first endpoint of the interval, that gives me 18. Now, if I substitute in the other endpoint, f dash of 6 gives me 48. So what all of this tells me is that this is the minimum value of the gradient of this function on this interval, and 48, that's the maximum value of the gradient of this function on this interval. So what this means in terms of our graph, it means when x equals 3, that's when the function is decreasing the most, and at x equals 6, that's when the function is increasing the most on this interval, only on this interval. If I were to keep drawing this function, it would have a larger gradient, over here at, say, x equals 20. It would have a more negative gradient at, say, at x equals minus 20. But this is the minimum value of the gradient and the maximum value of the gradient of this function on this interval. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.